Now, the third type of correction within sort of the basket of this first category is known as false discovery rate, or FDR. Now, crucially, FDR is doing something very different than the family-wise error correction. As I said earlier, the family-wise error correction, be it Bonferroni or cluster correction or any other type of family-wise error correction, those are saying, out of all the tests that I'm making, all the 100,000 to 200,000 tests I'm making, out of all this family, at most, I'm going to have 5% false positives. FDR is saying something very different. FDR controls the expected proportion of false positive among the suprathreshold values, meaning as opposed to controlling the number of false positives among all my tests, it's controlling how many false claims do I make. Let me explain it differently. So 0.05 family-wise error means there is only a 5% chance that any result is a false positive. Now, piece more than 0.05 FDR means out of all the voxels that I'm showing you in this nice picture that are active, at most 5% of those are false positives. So FWE is controlling the number of false tests. FWR is controlling the number of false claims. Because I show you a picture and there are all these voxels active, and I'm claiming that all the active voxels are meaningful. But 5% of those, no more than 5% of those are actually false positives. Okay, so it's very important that you understand the difference in the interpretation of a family-wise error correction versus an FDR correction. Now, whereas, for example, the cluster correction with random field theory is a very theoretical sort of way of implementing correction, FDR is particularly algorithmic. And it goes more or less like this. And this is, by the way, there are at least a couple procedures of doing this, but I will focus on the Benjamini-Hochberg procedure because I think it's the one most often used in fMRI, if I remember correctly. And the idea is the following. Say that you have 100,000 voxels. Order those voxels by their p-value and order them, and that's what I'm showing in this picture right here. So on the x-axis, it's the number of voxels. So voxel 1, voxel 2, voxel 3, or rather the number of p-values going from the lowest to the highest. And on the y-axis, I'm showing the actual p-value. Okay, so that's why the p-values kind of go like this. These are really low p-values. I've put here the very low p-values, and then I've put sort of more and more to the right the higher p-values. Okay, so they're all ordered in a nice line. Now, how do we determine which voxels are significant in FDR? Well, very simple. We take the first I voxels, so in this case, let's see, 1, 2, 3, 4, 5, 6, such that the p-value of the last voxel that I call significant, so the sixth in our case, is smaller than the number of voxels that I'm declaring significant, 6, divided by all the voxels that I have, 100,000, times alpha. So in other words, and then what you do is all the voxels from 1 through I, from P1 to Pi, you call those significant. So you reject the null for those voxels. In other words, one way of seeing it is that we're weighting in terms of the correction that we're doing. So this is 0.05. The correction that we're doing is weighted by the number of voxels that we declare significant, I, and scaled by the total number of voxels that I have. So if you think of the extremes of this, if I were to reject only one voxel, so this would be one, the p-value would have to be smaller than 1 over the total number of voxels, 100,000, times alpha. In other words, if I rejected only one voxel, FDR would be equivalent to doing Bumferoni, right? Because it would be alpha times 1, since only one voxel is significant, divided by 100,000. So alpha divided by 100,000. That's the threshold that I'm imposing. On the other hand, if I were to declare significant all the voxels inside the brain, so I would be equal to V, and then it would be tantamount to doing an uncorrected thresholding, because it would be V divided by V, 100,000 divided by 100,000 times alpha. So the p-value would just have to be smaller than 0.05. So in this sense, FDR is a flexible, the amount of correction that you're doing actually depends on how strong the effects are inside in your data. So now let's use some simulations to compare how these different approaches perform. So if you've never used simulations, here's what we're going to do. We're going to conduct 10 different experiments. Each column here is an experiment, and here's how we generate the data. So first, we set the signal. So see this, each square is our data set, and the white part is where the signal is, and the gray part outside is where there's no signal. Okay? So this is our signal, and we are setting the ground truth. Okay, this is where the activation is, and it's this big. Okay, then in each of these 10 experiments, we add some random noise. Okay? So our data are signal plus noise, and they look like this. So these are the data for experiment 1, experiment 2, experiment 3, et cetera, et cetera. So the question now is, if we take these data, which are signal plus noise, and we were to apply the different thresholding procedures, how well would we recover the real signal? Right, that's the question. If we threshold these using these different, if we threshold these data sets using these different approaches, how well are we recovering the real signal? And how well are we getting rid of all the noise that is out here? Okay. So I'm just showing them, here they're shown at an alpha of 0.1, so 10%. And so if you look at these experiments, so first you'll notice, see the red line? That is just showing the boundary of where the signal is. Okay, so if we got a perfect thresholding, what should happen is that we get a perfect circle that coincides, or rather, where the red line is its perimeter, and then everything outside would be black. Okay. So instead, as you see, that's not what happens here when we use no control for multiple comparisons. In fact, in this first experiment, if we use 0.1 as a threshold, what do we see? Well, we see that we get 11% of false positives out here. We kind of get most of the voxels or the pixels where the signal is, but we're also getting a lot of significant voxels out here, which we know are false positives because we set what the data are in the first place. And if you look through the experiment, that is true every single time, right? We're getting, every time we're getting somewhere around 10% false positives. But overall, I have to say, we certainly are getting most of the signal. It's just we're also getting all this stuff out here. Right, so on average, 10% of false voxels are incorrectly declared active at each individual experiment. Now, if instead we used a family-wise error rate, it would mean that we would really, really crank up the level at which each of these pixels has to be significant in order for us to declare it active. And what you see is that indeed, we get only, out of 10 experiments, we get only one family-wise error. Can you see it? It's tough, huh? You gotta squint real hard. It's here. Look, it's right there. I don't know if you can see it. See the little dot? There is one voxel out of 10 experiments. One time we had one false positive, exactly 10%. Everywhere else, you'll notice there's never a false positive. So that's exactly what the family-wise error correction is doing. It's saying out of all my tests, I want at most one false positive, in this case, 10% of the time. However, you will also notice that if you look inside where the signal is, there is no, we're getting a lot of false negatives. Right? And this is your typical Bonferroni at play. Right? It's way too conservative. And finally, we could do an FDR. And if you did an FDR on these exact same data, you would see that FDR is, in a sense, kind of a compromise between the two. However, at each experiment, just about an average of 10% of the voxels that are declared active, see the voxels in here plus the voxels out there, as you can tell, just about 10% of them are actually false positives. So 10% of the claims that we're making, 10% of the white voxels that we are saying, ooh, these are significant, 10% of those are false positives. So we're getting a fair share of false positives now. However, you'll also notice that we're getting a good number of pixels inside where the signal is. So we are recovering the signal, but at the price of getting false positives.